Welcome to the principle of superposition of waves and the formation of stationary waves. So here we are in a simulation that can demonstrate waves on a string. We have an oscillating end and we have a fixed end. And we're going to send a pulse through this string and watch what happens when it gets to this fixed end over here on the right. Okay. So it reflected. We sent a pulse through in the positive direction, and when it reflected, it came back in the negative direction. Let's look one more time. Okay, so reflections on a wave are in the negative direction to the initial wave. And what this means is that if we send a continuous stream of pulses through this string, we're going to get a continuous stream of negative displacement pulses as reflections. And when these cross over, they add together and can cancel each other out. So for a moment there, after the first pulse reflected, it cancelled the second. Let's look one more time, this time in slow motion. There's the first pulse. Here's the second. The first one reflects, and for a moment, we have a straight line. So if I set this to oscillate and send a continuous wave of positive and negative peaks through this string, when they get to the other end, they're going to reflect and they're going to cancel the opposite peaks coming the other way. And if I set this just right, I should be able to create something called a standing wave. And there we have a standing wave. So it's a wave where you appear to have locations that are not moving and locations with maximum displacement. So we've got a node over here, a position that isn't moving, and the oscillator represents another node, and then in the very center of those two we have a position of maximum displacement called an antinode. This is the lowest frequency at which this will work. If I double the frequency, I can create another standing wave. So we have a frequency of 0.43. Let's change that to 0.86. And I'll pause it there, and you can see that we have a waveform. It looks like a regular sinusoidal waveform, but it's oscillating between this position and that position. We have a node in the middle now, where previously we had an antinode, and we have a node at each end, and in this position and this position we have an antinode. And it oscillates about these locations. Notice that this node in the middle is approximately stationary. This is the position of minimum displacement. Let's have a look at one more, and then we'll look at the mathematics. Okay, so here is the next standing wave, and you'll notice that we've got 3 loops this time. The first one we had 1 loop, the second we had 2 loops, and the third we have 3 loops. And it oscillates with these nodes approximately stationary and the antinodes showing maximum displacement. So it bounces between this position and this position. And we've got those 3 loops. Let's have a look at the mathematics of standing waves. So the first standing wave that we had was a single loop with a node at each end. Node, node, and an antinode in the middle with that maximum displacement. And it made a loop that looked like this. Now the frequency of this first standing wave is given by the properties of the material that's being oscillated. So that's the properties of the material of the string. And we have this equation. So the inverse of twice the length and the square root of the tension in the string divided by the mass per unit length. So this L here is the length of the string, the length. We have the tension or the force on the string, and often when you're creating these standing waves, you have a fixed point here. We have the string oscillating, and that string is held over a pulley with a mass hanging from it there, and an oscillator generating this wave, usually at this position. So an oscillator vibrating this up and down. And the tension is the force created by that mass. This term here is the mass per unit length, and that's the string itself. So how many kilograms is 1 meter of that string? So a heavy string will have a large mass per unit length, and a thin string, like cotton for example, would have a low mass per unit length. Okay, let's have a look at some of the mathematics of the different types of standing waves that we can get on a string. Okay, so the first shape that we have is that one loop. Now the length of the string, that distance there, is equal to half the wavelength of a wave. Now remember that one wavelength is given by that shape there, or maybe you could draw it as being from a peak down to a trough and then back to a peak again. Personally, I prefer that. And this shape here is from this position to that position. So that is half a wavelength. So the length here is equal to half a wavelength. And we can also write that as being that the wavelength is equal to 2L. So one of those, you would need 2 lengths of string in order to achieve that. Now this we refer to as the first harmonic, with frequency F1. Now, because we're going to keep the string the same throughout this experiment, we can increase the frequency of the oscillator and we can create more loops, but the velocity of the wave in the string is going to be constant throughout the experiment. And we know that velocity is given by the wavelength multiplied by the frequency. So we're going to use this equation and our understanding that this value is constant to help us in future calculations. So we're going to substitute in 2L for the wavelength, and we're going to substitute in the first frequency, the first harmonic, for our value for frequency. And this is our value for velocity that we're going to use in subsequent loops. So the next one that you can have is you have a node at each end, and you can have a node in the middle where previously we had an antinode. So that means that we now have an antinode here and here. And we now have 2 loops. So this is the next one up. The length of this is equal to the wavelength, because we have the entire up, down, and back to the start again. So the wavelength is just the length of the string. The frequency of this standing wave is going to be given by the velocity divided by the wavelength. Now, it may be that this is the second harmonic, but we need to work out if that's correct or not, because it's not always the case. So we're just going to confirm whether or not we can call this the second harmonic. So what we're going to do is we're going to substitute this in for velocity, and we're going to substitute L in for wavelength. So we're going to use our frequency for the first harmonic to understand whether or not this is the second harmonic and whether we can call it that. So the wavelength is L, and now we're going to cancel. And the frequency of this standing wave here is equal to twice the first harmonic. So this is actually the second harmonic. So this is the second harmonic. All right, on to the next one. We have a node, and we have two nodes in the middle this time, and another one on the end. So loop, loop, loop. The length of this string consists of a full wavelength and then another half a wavelength. So that makes 1, 2, 3 halves. And conversely, we can also write this. Frequency, again, is given by this, and we're going to substitute in the first harmonic values to work out if we get the same sort of relationship, the same pattern. And this time the wavelength is this, which we can cancel. And if you study algebra, you'll see that we get this outcome. So 3 times the first harmonic, this is the third harmonic. So we can call this the third harmonic. And if you notice, there is a pattern here. So if we were to just add a few bits and pieces in here, let's change this fraction. Instead of having it be 2, let's change it to 2 over 1. And you'll notice that this is 2 over 3, because this one in the middle is 2 over 2, which of course cancels as a 1. But if we think of it as being 2 over 2, then what you see is that the number at the bottom of the fraction, the denominator, is actually the same as the harmonic value. So that's one way of remembering it. A string, it might be something like a violin or a guitar. And we're going to look next at closed tubes, which would be musical instruments like oboes, for example. Consists of an oscillator at one end of a closed tube and an open end on the other side of the instrument. And what you have is you have a node at the closed end and an antinode at the other end. You can have nodes and antinodes in the middle, but the lowest frequency that you can get is going to have a node at this end and an antinode at the other. So the first harmonic is going to have to be a node and then an antinode. The length, again, there, is part of a wavelength. Let's draw the wavelength on again, because that I always find is very helpful. And we can see that we've got this part of the wave, which is only 1/4. So the length is 1/4 of a wavelength, which can be written that the wavelength is equal to 4 times the length of the string. and this would be the first harmonic. Let's work out what the velocity would be on this string in terms of the frequency of the first harmonic and the wavelength of that first harmonic. So we know that velocity is equal to the wavelength multiplied by the frequency, which in this case is 4L multiplied by the first harmonic. So that is the value for velocity that we're going to be using. And remember that the reason why we use this is that the velocity of the wave inside this tube has no reason to change. Unless, of course, you do something silly like you take the instrument from a warm room into a cold room. But if you're doing a scientific experiment, you want to keep all of the variables as similar as you can possibly keep them. You want to keep things like that the same. And the velocity, therefore, should not change. Okay, so in our next standing wave, we can introduce another node into the center. So we're going to get an antinode at this end, and we're going to get another node. So we're going to have a loop and then an open. There we go. So that is the next most complex standing wave that we can get. And the length, this is one loop and then down to the antinode. So this is 3/4 of a wavelength, which can be written in terms of the wavelength as being 4/3 of the length. The frequency of this harmonic is given by that equation, and we can substitute in the velocity over the wavelength and then do some cancelling, which gives us the third harmonic. So this is not the second, this is actually the third harmonic, and this is one of the reasons why we're doing this bit over here, just to check. If we were to change this, if we were to change the oscillation frequency to 2 times the first harmonic to try to get the second, it would not produce a standing wave. So this doesn't work in this situation. That's why it's so important to check that we are getting the harmonic that we think that we are. So this is the third harmonic. The next most complicated standing wave that we can get in this setup is we can add another node into the middle. So instead of one full loop, we now have 2 and a bit. The length of this is, so there's one wavelength, and then we've got a little bit more, but how much? So if we have a look at this diagram, we've got one full wavelength, and then we've got that much more, which is 1/4. So we've got one full wavelength and another quarter, which is 5/4 of a wavelength in total. In terms of the wavelength, that's 4/5. So the wavelength is 4/5 of this length. Let's calculate the frequency in terms of, so the velocity in terms of the first harmonic has that value, and then the wavelength has this value. Cancel. So this is actually the 5th harmonic. This is actually the 5th harmonic. Okay, so the closed tube is a little bit strange. We don't have the even number harmonics. If you were to set up an oscillation frequency to try to get, for example, the 4th harmonic by calculating, well, what's the first harmonic times that by 4, let's put that in, you just wouldn't get a standing wave. It wouldn't happen. So it's only the odd numbers that work in this situation. Let's have a look at another type of standing wave and another type of musical instrument. So the last type of standing wave we're going to have a look at is created in open-ended tubes. For example, recorders. This is where you have a tube that's open at both ends, and you have an antinode at each end, and you can add nodes into the center to make the standing wave, to increase the frequency of the standing wave. The most basic version that you can get has an antinode, a node in the center, and then another antinode. Okay, so this is going to be the first harmonic, the most simple. Let's redraw our wave up here, which has been quite useful so far. And let's start considering how the wavelength compares to the length of the tube. So we have the length of the tube, and this is the top, middle, and the bottom part of the wavelength. So if we split that into quarters, we can see that it's 2 quarters, with this one at the end and that one at the other end sort of missing, having been chopped off. So this is half a wavelength. And if we write that in terms of the wavelength, one wavelength will be twice the length of this tube. And this is the simplest frequency that you can get, the simplest standing wave, and therefore the lowest frequency. And if we calculate what the velocity would be in terms of wavelength and frequency, then the wavelength of this frequency is 2L, and we express the first harmonic's frequency as being F subscript 1. Okay, if we make this a little bit more complicated, just a tiny bit more complicated, we would be adding a node into the center. So we'd have 2 nodes in the center instead of just 1, and we'd have an antinode at both ends. Okay, the length of this, so let's have a look. We're going from the top down to the trough, which is this bit here, and then we're going from the bottom to the center, which is this bit here, and then we're going from the center to the peak, which is actually that bit there. So we are going through one full wavelength in this example. So the length is one wavelength. The frequency, which is given by the velocity over the wavelength, we're going to substitute this in. And then cancel. So this frequency is twice the first harmonic. We have the second harmonic. So this looks like it's not following the pattern of the previous, and it's pretty straightforward. But we never can tell, so we're going to continue to do our calculations and be hesitant before we make assumptions. The next most complicated is going to be adding one more node into the middle. So let's draw 3 nodes. And we've got an antinode at the end. Loop, loop, open. There we have it. The length here, we've got peak, trough, back to 0, back to a peak. So that's one full wavelength. And then we've got this section here, which is a half a wavelength. So we've got 1.5 wavelengths, one full wavelength, and another half is 3 halves. And in terms of length, that would be 2/3 of the length is one wavelength. The frequency is given by this, which we substitute the first harmonic into. And this wavelength, cancel. And we get this harmonic being 3 times the first harmonic, which means that we have the third harmonic. And then we have it. So this is the mathematics of standing waves. We're going to have a quick look at a couple of practical applications of standing waves now, where we can do some calculations and compare our answers to expected values. So the simulation that we looked at was looking at oscillations driving a standing wave on a string. And that's a practical that you may very well be doing in the classroom. Here is another practical that you can do for standing waves. We have this piece of kit here on the left, and then we have a practical that can be done at home if you like, but make sure that you are safe, and I'll give you a few pointers for health and safety. So here we have a microwave emitter, and here we have a microwave detector. And if you switch on the microwave emitter, you can create microwaves that travel through the air, hit the metal plate, and reflect to create a standing wave in the middle. And the detector can be placed at different positions between the emitter and the plate, and the reading is on this dial. So the strength of the microwaves can be read off this dial. If the strength falls to 0, you know that you are located at a node. If the strength reaches a maximum, you know that you are located at an antinode. And by moving the detector up and down between these two pieces of equipment and taking measurements using a ruler, you can record the distance between nodes and antinodes, and therefore calculate the length of the wavelength and investigate the wave. You can do something similar using a bar of chocolate. Now, if you put a bar of chocolate into a microwave oven, having removed the rotating plate, then what will happen is that the chocolate will burn. So you have to be very, very careful doing this. Set it to its lowest power, switch it on for only a couple of seconds at a time, keep monitoring the chocolate to make sure that it's not burning and creating big plumes of smoke that are going to set off smoke detectors and get very hot and burn you. Just be sensible. So low power, a couple of seconds only, and what will happen is that the standing waves that are set up inside the microwave oven will melt the chocolate at different positions, and those positions are nodes. So this is a node and this is a node. So what's happening is that the wave inside the microwave oven, the standing wave, is oscillating and it's melting the chocolate first at those positions. And you can use a ruler to measure the distance between those nodes. So let's do that now. So we've got a very large melted spot over here and an extremely large melted spot over here. So it's very difficult to take accurate readings. I do think the ruler is approximately at the right place for this one. The 0 is roughly in the middle. But this location here, I reckon it's probably about there, which is, say, 5 point, or maybe it's over here, 5.6, something like that. So the distance between nodes, so node to node, is, let's say, 5.7 centimeters, and I reckon that I'm probably accurate, plus or minus 3 millimeters. That is an error of 5%. Okay, if that's node to node, then a full wavelength would be double that distance. So because we're doubling that distance, we're also doubling our error. So this becomes 11.4 centimeters with a percentage error of 10%. We can calculate the frequency because we know the speed of a microwave, which is the speed of light, and we now have the wavelength. So if we do this calculation, 3 times 10 to the 8 meters per second divided by 11.4 times 10 to the minus 2 meters, we get a value, and given that I've only measured it to 2 significant figures, I'm going to write my answer down to 2 significant figures. We get an answer of 2,600 megahertz. And if I have a look on the back of the microwave where this was done, I can actually pull out the statistics for this piece of equipment, and we see that it has a frequency of 2,450 megahertz. And the value on my calculator is within 10% of that number. So that was a successful measurement and a successful calculation.